Sarah Whitehouse. She's the first speaker of today's session, and she will talk about model structures and spectral sequences.
Okay, well, thank you very much. Thank you and solidarity to the organisers. They've put together a fantastic programme in very difficult circumstances. Yeah, and thanks to everybody for coming. I know everybody's juggling lots of difficult stuff. And yeah, I'm attending as much as I can of the programme. Apologies to any other speakers where I can't attend their talks. Maybe it's worth saying right at the start that this talk is a variant of one that I gave in Oates back in November, I think it was. So yeah, I'm going to be talking about some model structures on various categories which have associated spectral sequences. And the point is that in this situation, you see a kind of hierarchy of model structures related to the different pages of a spectral sequence. So my plan is this. So here's an outline. So I'm going to start with really brief but sort of basic introduction to model categories. So just to set the scene a bit, and for graduate students who are new to this kind of topic, and so on. And then I'll say a little bit about spectral sequences. I mean, I won't try to really tell you what they are or what they do if you don't know already, but I'll talk about category of spectral sequences, and I'll introduce quasi-isomorphisms, and the point is that those are going to be the notions of weak equivalence for these model structures. And then I'll focus in on multicomplexes. I'll talk about some other examples as well, but that's going to be the sort of main category where I'll talk about the model structures, and I'll give you the model structures and some ingredients. And at the end, say a little bit about comparing model structures as well. Okay, so let's just start with something really basic about model structures and the motivation for them. So if you haven't seen this kind of thing before, what you should probably have in mind some examples already. So the two I'll mention are firstly topological spaces with weak homotopy equivalences, so continuous maps of the space which induce an isomorphism on all the homotopy groups. So that's one example to have in mind, the kind of category that we're going to be talking about putting extra structure on. And then another one which is actually more relevant, it's more algebraic and it's more relevant for the kinds of examples that I'll talk about today, would be chain complexes and quasi-isomorphisms. So this time maps of chain complexes which induce an isomorphism on all the homology groups. So you want a good framework for thinking about things like topological spaces up to weak homotopy equivalence, or chain complexes up to quasi-isomorphism. So you would like to be able to think about the associated homotopy category where you invert those either weak homotopy equivalences or the quasi-isomorphisms. And so you would need a good way to do that, and also ways to think about lots of structure that you have in the underlying category. And that's what model categories do. So what they model is homotopy theory, which you might want to think of as infinity categories, if you're so inclined. And the kind of analogies that people give are that you can think of a model category, giving a model category for as underlying a homotopy theory, as something similar to giving a presentation of a group or giving a basis of a vector space, something like that. So it's making choices, but sometimes you have good reasons to make those choices in order to be able to calculate something or have good constructions of something, or for other applications. So that's the kind of thing that we're doing when we do this. So I'm not really going to define this for you properly, because that's a whole lecture course in itself. But the structure that you have, if you have a model category, so firstly you have a category, and then you specify 3 classes of morphisms in your category. The weak equivalences, W, so and I've written some sort of standard notation for how these morphisms are typically written. So we've seen those in the example. So when I just said that you might be thinking about topological spaces, and then the weak equivalences would be the weak homotopy equivalences. Or you might be thinking about chain complexes with the weak equivalences being the quasi-isomorphisms. And then you specify two other classes of maps, fibrations and co-fibrations. And I'm really not going to tell you about all the axioms that those have to satisfy. I mean, I've very briefly sort of listed a summary of some of the key phrases that go into the axioms. So the category should have small co-limits and limits. There's something called a 2 out of 3 property for the weak equivalences. So that means if you think about two composable maps, F and G, and they're composite, if any two of those three maps is a weak equivalent, then so is the third. And then all these classes are supposed to be closed under retracts. And then we get to the really perhaps crucial properties, which are lifting properties. And then there's also factorization properties. So there's a big list of axioms. And obviously in this talk, I'm not going to try to go through all of those. One important thing which is going to be relevant for the actual examples that I'll describe later on, is that although you usually sort of set up the definition in a sort of symmetrical way, if you like, by talking about all three of these classes, actually any two of the classes determine the other one. And that's something that we'll see in our examples. So specifically in our case, our cases, we'll be in the situation where we specify the weak equivalences and the fibrations, and we leave the co-fibrations determined by one of these lifting properties, namely the standard thing. So when I said lifting properties earlier, this is one of them, that the co-fibrations should satisfy the left lifting property with respect to maps which are both weak equivalences and fibrations. And those things are sometimes called trivial fibrations or acyclic fibrations. Okay, and I guess I thought I should perhaps just put up one diagram and say a word about what this LLP is. So that's the left lifting property. So what that means is when you have a commutative diagram like this, then having a lift in such a diagram is having an H here, making the triangles in the diagram commute, and you call that I having the left lifting property with respect to P. So let's just go back to one of the two examples that I had earlier and describe one of the very standard, straightforward kind of algebraic model structures. So let's go back to chain complexes. The most relevant for what I'll say later is unbounded chain complexes. And there's a standard model structure called the projective model structure. And it is something that sort of answers the thing that I said at the beginning about wanting a model structure on chain complexes with the weak equivalences being the quasi-isomorphisms. And then in this example, the fibrations are the degree-wise surjections. And this is sort of typical. I mean, if you're not familiar with this kind of thing at all, then you should sort of think that often fibrations will be some kind of surjections. And here they're literally degree-wise surjections, but often they'll be determined by some kind of surjectivity property. That's quite commonly what's going on in model structures, and we'll see that in examples I want to talk about later on. And then, well, I mean, we can say explicitly what the co-fibrations are here, but it's maybe a tiny bit more complicated than one might guess at first. So similar to what I was just saying about fibrations being some kind of nice surjections, often co-fibrations are some kind of nice inclusions or injections. And well, this is exactly what they are here. But already we see, even in this example, that you might just want to say that the co-fibrations are the things that have the left lifting property with respect to the trivial fibrations, rather than having to specify them explicitly. Okay, so that was a very brief introduction to model categories in the sense that I want to talk about them. So then the other main ingredient of what I want to talk about is spectral sequences. And I'm going to say what I mean by that. So here at least, we're going to fix a ground ring. So A is going to be a commutative unit or ground ring. And the spectral sequence will be a spectral sequence in A modules. You could probably do this in some other abelian category, but let's stick with this. So what is a spectral sequence? So what's the data? The data is that you have the pages of the spectral sequence. So for each R, you have a bigraded A module, which is the rth page of the spectral sequence. I'll write ER, that's typical. And then you have a differential on the rth page called the rth differential. I'm writing delta R for that. And well, I've got some choice of convention for the bi degree. Other conventions are available. And this thing is a differential. So if you square delta R, then you get 0. And then we should have an isomorphism between the homology of the rth page with respect to the rth differential and the next page. So that's what a spectral sequence is. It's all that data. Of course, if you haven't ever seen one before, it wouldn't be at all clear what the point of all this would be. I mean, they're major tools for computation throughout lots of areas of mathematics. And the idea is that in lots of settings, these pages of the spectral sequence give you successively better approximations to something you want to calculate. So that's why people care. And we can make a category of these. So a morphism of spectral sequences, I haven't written it out in full detail, but it's kind of the obvious thing. It's a sequence of morphisms of the pages compatible with all the data that I wrote. So compatible with the differentials and with the specified isomorphisms between the homology of one page and the next page. Okay, so that's how I'm thinking about spectral sequences, a category of spectral sequences. So in that case, I want to move on to thinking about the fact that there are lots of categories that have associated functorial spectral sequences. So I want to think about categories C, where we have a functor to this category of spectral sequences that I just described. And now I'm not writing all the data, but so associated to an object in C, there should be a spectral sequence in the sense of the previous slide. So in particular, an rth page with an rth differential for every R and some more stuff that I haven't written here. And this is functorial. So for every morphism in the category, you get an induced morphism of spectral sequences. So in particular, a morphism on the rth page for every R. So you probably know some examples of this kind of situation. Maybe you know lots. So the ones that are kind of that I want to talk about here, and the ones that I've studied with subsets of the long list of co-authors that I had on my front page, are these ones. So this is probably the one that people maybe first meet when they first study spectral sequences. They think about a chain complex or co-chain complex with filtration, and there's a standard associated spectral sequence to a filtered chain complex. Another very standard situation is the category of bicomplexes. Indeed, really, there are sort of two different standard spectral sequences that one might associate to a bicomplex according to whether one does kind of row filtration or column filtration of a bicomplex. But those two situations are completely related by an obvious symmetry, and one may as well just fix a choice and consider one of those two spectral sequences. And then I've mentioned here multicomplexes, and this is actually the example that I'll focus on the most here. So I'll say something about what these are. These are probably a little bit less familiar if you haven't, lots of people maybe haven't worked with these so much as the first two examples. And I'll talk about what they are and also truncated versions of them. And the truncated versions, one particular case actually recovers the case of bicomplexes. So we get bicomplexes as a special case of a multicomplex, a truncated multicomplex. Okay, so there are obviously lots and lots of other examples, and people may be interested in other examples, other kinds of filtered objects in other categories that give rise to spectral sequences. And one can certainly ask how much of the story that I'm about to tell can be done in other settings, which is definitely a question that I'm interested in, but I'll focus on these examples here. All right, so we've got some idea about model category, we've got our spectral sequences, we're thinking about some category which has functorial spectral sequences. So we get this very natural notion of E-quasi-isomorphism. So for any non-negative integer R, we can think about a morphism in our category. So we're in any one of these categories C here. And we can declare it to be an E-quasi-isomorphism if the map that it induces on the R page of the spectral sequence is a quasi-isomorphism. Or equivalently, if the map it induces on the R plus first page is an isomorphism. So this is the kind of situation that I want to think about. And you can definitely, well, it's reasonable to think about these as potentially the weak equivalences of a model structure, because they have good properties listed there. This class of morphisms is closed under composition and it contains isomorphisms, and it satisfies the 2 out of 3 property that I mentioned, all kind of obviously because it's defined by some induced map being an isomorphism. So these are reasonable things to think of as potentially, well, as weak equivalences, and therefore potentially the weak equivalences of a model structure, and that's what we want to do. We want to find some model structure where these are the weak equivalences. This is the way the inclusions go. So the condition is weaker and weaker as R increases. So you have more and more of these quasi-isomorphisms as you increase R. Okay, so let me just really briefly mention some examples, like where these things have come up, in order to just motivate a little bit and say that potentially these are interesting model structures to look at and so on. So actually these comments will be about filtered complexes, because that's the case that has come up before more than others really. So in filtered complexes, I mean, roughly speaking, the R equals 0 case is a kind of classical thing that people have studied in looking at filtered complexes. So what they would normally do, or what has often been studied in the past, is morphisms which restrict to a quasi-isomorphism on each stage of the filtration, and that's the same thing as these 0 equivalences if you have, well, so it depends on conventions, but say if you're doing increasing filtrations, if they're bounded below, then that would be the same as the R equals 0 equivalences. So this R equals 0 model structure is sort of classical, or close to something that would be classically considered for filtered complexes. And then things that sort of are only well defined up to, well, now I'm thinking about R is 1. Those things have been around for a long time in the context of mixed Hodge theory. So there's something called the weight filtration there, and that's only well defined up to E1 quasi-isomorphism. So you're already seeing some structure there that only makes sense up to the next level of quasi-isomorphism, rather than the 0th level, I guess. And then the higher R things had been looked at before the sort of recent work that I'm really talking about here. so in particular, sort of in the context of rational homotopy theory, these E-quasi-isomorphisms, Halperin and Tonray had looked at these and sort of developed a kind of theory of minimal models for filtered DGAs, and sort of developed a theory of filtered homotopy type, or rather a hierarchy of theories, one for each R, with these ER quasi-isomorphisms. They didn't have a model structure though. They were sort of developing some of the theory, but without having an underlying model category structure. And they had useful applications nonetheless in this context. So one could view what we're doing as supplying a model structure into which some previous work fits. Okay, so that was to motivate a little bit why some reasons to care about these different model structures, including for the higher R. All right, so let's just come back to our functorial spectral sequences. So, I mean, so far as part of the definition, I had these functors for the rth page, but of course, because we're specifying that each page is the homology of the previous page, you can kind of separate that out into kernel and image of the previous differential, and write, as usual, the R cycles and R boundaries, and those are also functorial. And the reason I'm bothering to say that is that it's actually going to be important for the model structures that are coming up, that we have freedom of choice here. So one could make different choices. So we could replace the R cycles and the R boundaries by other functorial choices if we wanted to, up to isomorphism, as long as we do it in such a way that we still get the same quotient. So the rth page is unchanged up to isomorphism. So that's going to be a freedom that we will make use of in setting up the model structures. All right, so I'm now going to tell you a bit about what multicomplexes are, give some definitions and a bit of some examples, special cases examples, a little bit of motivation, try to very briefly say why people are interested in these, at least some examples of why they are, before then going on to talk a bit about the model structures that we have on this category of multicomplexes. Okay, so this is another place where obviously different conventions are available. So the ones that I'm talking about, for me, multicomplex, firstly, it's a bigraded A module. So again, everything is in modules over some commutative unital ground ring. Possibly you can do everything in some other abelian category. So they're bigraded, and the grading, Z grading in two directions, so unbounded. And you have a whole bunch of structure maps, an infinite family of structure maps indexed by non-negative integers I, so a di for each such I, some convention for bi-degrees for those maps, and satisfying an infinite family of relations as written there. So we have a relation that some alternating sum of di dj is 0, and we have such a relation for I plus j equal to L for every non-negative integer L. So just to spell it out really concretely, what it looks like in low values of L, the first few of these relations. So the very first one says that d0 squared is 0. So d0 is a differential. And then the next one says that d0 and d1 commute with each other. And then maybe the one that I want to emphasize is what this relation indexed by L is 2 says here. So, I mean, firstly, what it doesn't say is that d1 squared is 0. So d1 is not necessarily a differential. But it's saying that d1 squared is, well, d0, d2 plus d2, d0. So thinking about d0 as a differential, which it is, what this is saying is that d1 is a differential up to a homotopy, a specific homotopy specified by d2. And, well, I'll come back to this and make this a bit more precise in a second, but what the higher relations that I haven't carried on writing here capture is the higher homotopy coherences for this situation that I've just described. So we've got an underlying differential that we're using as a differential, and then we've got some other structure map which is a differential up to homotopy, up to specified homotopy, and then we would have higher homotopy coherences for that situation. And this is what a multicomplex is. And I mentioned before that I also want to talk about some truncated versions of this structure. So these are just subcategories. So I'm going to, again, for a non-negative integer n, I can think about an n multicomplex. And it's just a multicomplex where after, or from n onwards, all the structure maps are 0. So we're just looking at special cases where the higher structure maps are 0. We can do that for each n. I'll give examples in just a second, which will perhaps help fix ideas of what's going on here. So we can think of multicomplexes themselves, the non-truncated thing, as the case n equals infinity. And then, well, I want a category, so I better tell you about the morphisms. And for those who know why I've said it, I'm talking about the strict morphisms of n multicomplexes. So this is just a map, well, of underlying bigraded modules for a start, and then commuting with every one of the structure maps. It's probably what you would guess. And that thing I've just put up there is just notation. So this is what we're going to write for the category n multicomplexes of A modules. Okay, so these are going to be the sort of main focus of what I'm going to be talking about. I'm going to be talking about some model structures that you can get on this category for each n and related to some stage of an associated spectral sequence. So let's just go through some special cases to help fix ideas and maybe make more precise the thing I said about higher homotopies a moment ago as well. So if we had a 1 multicomplex, so that means we've just got a D0. With my conventions, that's a vertical differential going up. So you've got a bigraded thing, but it just has a vertical differential. So we call these vertical bicomplexes. So bicomplexes, but the horizontal differential is 0. And then the next case is bicomplexes themselves. So if you only, in this case, we've got a D0 and a D1. And because D2 is 0, D1 now actually is a differential, and this is exactly a bicomplex. This is coming back to this thing I mentioned before. So a multicomplex is a homotopy coherent version of a bicomplex. So I can make a really precise kind of operatic type statement to make that precise. And indeed, this is a very sort of simple and nice example of such a thing. So to get the version with the conventions that I've given here, you would work in the category of vertical bicomplexes. So this one up here, where you have bigraded things with a vertical differential. And then you would take the operad of dual numbers. That's an operad that just has a single generator, which you might as well call D1, because that's how you're thinking of it, and a single relation, which is that D1 squared is 0. And then if you take the algebras for that operad in vertical bicomplexes, that gives you bicomplexes. Your D0 is in the underlying category and your D1 is in the operad. and they're compatible. And then you use standard operatic machinery to make the infinity version of the operad, the one that controls the homotopy coherent algebraic structure. And if you do that, then algebras for the infinity are exactly the multicomplexes. So that's making precise the thing about it's a homotopy coherent version of a bicomplex. Okay, and then, well, I just want to talk through some places where these have come up and try to give maybe a little bit more motivation or intuition for what these objects are and why one might be interested in this category of multicomplexes. So at least among the first instances of these that one can find in the literature is some work of Wall, a long time ago, early 60s, talking about, well, group cohomology, essentially. So the question is, how do you build a resolution for a group extension, imagining that you have already your hands on some kind of resolutions for the two groups. You want to build a resolution for the extension group. And multicomplexes kind of come naturally there. There's sort of a way of building a resolution for the extension group out of the two pieces. And the form that it takes here is tote of a multicomplex. So there's a natural multicomplex structure coming there. And well, so that appearance as kind of resolutions in a certain setting was developed a lot by, in particular, Guggenheim and May and others in the 70s. So that's the kind of situation where you see multicomplexes. You know, you already have some differential graded object, and then you want to resolve that, and you get multicomplex resolutions in that setting. So, well, lots of other people have worked with these for these kinds of reasons, really. They're giving resolutions of differential graded objects. So that's why they're appearing in lots and lots of places. And then the other one that I maybe wanted to talk about a little bit, this is kind of how I really got interested in thinking about multicomplexes. It was some work of Stefan Sagava, which is really a kind of multiplicative enhancement of the story that I've just been talking about, sort of resolutions of differential graded objects. He introduced the notion of a derived A-infinity algebra. Some related structures had already appeared, for example, in the work of Lapin. And yeah, these can be thought of as, well, a multiplicative enhancement of the story I just told. So if you have not just a bicomplex, but a monoid in bicomplexes, and you think about the kind of structures that arise there, you're led to these derived A-infinity algebras. You can, roughly speaking, think of them as a kind of mix of multicomplex and A-infinity structure. So we've got sort of both a differential up to homotopy and an associative multiplication up to homotopy, kind of interacting with each other. And that's roughly what's going on in this story. In any case, I'm not going to get into that multiplicative story here, but each of these structures has an underlying multicomplex. And to understand the homotopy theory here, what I and others realized was you kind of need to understand more about the homotopy theory of the underlying multicomplexes, and in particular this kind of hierarchy of different notions of equivalence related to a spectral sequence appears. All right. Okay, so now I'm going to tell you how a multicomplex has an associated spectral sequence and say something about it. Well, I mean, it has an associated spectral sequence because it has an associated total complex with a filtration. And so that puts you in the situation of standard situation of filtered complex where you have an associated spectral sequence. Now, I'm going to say a little bit about the details of this. And this relates to joint work with Muriel Livenet and Stephanie Ziegenhagen. So we have a short paper where we give explicit descriptions of this spectral sequence associated to a multi-complex. So you can explicitly describe the R cycles and the R boundaries and the differential on the R page in terms of the structure of a multi-complex. The differential on the R page, for example, it involves the structure maps indexed by 0 up to R. Now, I'll show you some formulas, but not too many, I hope. And then after I've shown you some formulas, I'll show you some examples. So maybe that will help to see what's really going on. So, so I'm going to just tell you about the cycles, and I'm going to kind of suppress what happens with the boundaries. So for the cycles, well, the 0 cycles, that's just the object that you started with. And well, so this looks a little bit complicated. And as I say, I'll show you a picture and some examples in a moment. What are the R cycles? Well, you specify an element in the relevant bi-degree, and then they're determined by the existence of a family of other elements, R minus one of them, offset, sort of diagonally offset from the one where you started with, and satisfying a family of relations which says that an alternating sum of differentials on these elements should be 0. And there's a family of R relations. So that probably, unless you're very good at absorbing things like this, maybe just looks like some horrible formulas. I'll show you in a moment what this looks like in some examples. Right, so what I just said was about ZR. I'm not going to tell you explicitly about BR, but that you can also write down formulas really explicit, such that obviously the rth page of your spectral sequence is the quotient, and then you want to specify the differential on that R page. And then, well, there's a formula which is really reasonably simple. So an R cycle is going to be a class of an A0, as on the previous slide, and you can just specify which class it gets sent to as an alternating sum of the D's applied to these A's which had to exist. And of course, there's things to check, like this formula is well defined, independent of the choices involved. So I guess I gave formulas for the general case of multicomplexes, but you can just restrict to n multicomplexes. That's just setting some D's to be 0 in these formulas. You just restrict to that case. And if you restrict to the case n equals 2, which was the case of bicomplexes, then these formulas are just really well-known things. How do you describe explicitly what's going on in the spectral sequence associated to a bicomplex? Well, one of the 2 standard spectral sequences, and the one I mean is, we'll see in the examples, but I've got a vertical differential and a horizontal one, and I'm doing the vertical differential first. So that's the spectral sequence of the bicomplex that we've chosen here. Okay, so let's have a look at an example. So not sure if you can see the title up here. It's maybe hidden for me. It's a bit hidden under things. But what this says is that I'm going to look at the case n equals 2 first. So that's the bicomplex case, so quite familiar. We'll go up in a moment. And then this says that I'm going to look at 3 cycles. So that's what we're doing. And then this up here is just showing you my conventions. So we're doing bicomplexes, as I said. So we have just a D0 and a D1. like this, D0 going vertically up and D1 going horizontally left. Okay, and then what's a 3-cycle? A 3-cycle, well, it's going to be an A0, say here, and it has to, D0 of it has to be 0. D1 of it doesn't have to be 0, but it has to be D0 of something. And then similarly, that something, D1 of it doesn't have to be 0, but that has to be D0 of something. So they have to exist A1 and A2 like this. And then in that situation, the delta 3 on the 3rd page of the spectral sequence, we've kind of got one bit of data left, which is the D1 of the A2 here. And that's what delta 3 does. It takes the class of A0 to the class of, well, up to sign the class of this element here. So this is completely a standard thing in bicomplexes, but I'm kind of doing it as a warm-up and in order to show you a little bit what happens as you put in the extra structure maps, and also later as we modify the cycles in order to get our model structures. All right, so what's happened here? What's happened on this next slide is that I've put in one more structure map. So we're still thinking about 3 cycles, so the same situation as before in terms of which stage of the spectral sequence I'm thinking about, but I've put in one more structure map, and with my conventions it goes like this. So I've got a D2 now. So what happens is that there's now room for a couple of D2s here, and so one here and one here, and a 3-cycle here. It's still an A0 such that there exists an A1 here and an A2 here, and the formulas just change a little bit. Nothing changes here because there's no room for anything extra here, but here we now get a formula that D0 of A2 is something involving kind of the 2 possible things it could involve. The one you had before, which was D1 of A1, but now also a D2 of A0. And similarly, the formula for the differential kind of gets modified in a fairly obvious way by the kind of extra thing that you have here coming from the fact that you have now a D2. So that gives some kind of feel for what happens maybe in the case of 3 cycles at least, and putting in at least one of these extra structure maps that we have in multi-complexes. And actually, I mean, that's almost the full story for 3 cycles because there's not much room for anything else here. So I could put in a D3, and it doesn't matter whether there's a D4 and D5 and so on for the story for 3 cycles because there's kind of no room for them in the picture anyway. The one thing that changes is that now there's room for a single D3, and the only place it can kind of appear is in the formula for the differential, and that's where it appears. So this is telling you about 3 cycles in the general multi-complex case now, about 3 cycles and what the differential looks like. And this is just intended to kind of give you a flavour for what these formulas are doing, and the fact that you can kind of specify everything explicitly. Okay, so I'm going to talk about the model structures, and so here's probably the main theorem that we have here, and so I'll talk through this. Afterwards, I'll make some comments about this, and then tell you some of the ingredients that go into the model structure. Certainly not a proof, but maybe the key idea that comes up. Okay, so let's talk through the theorem first. So and it's joint with the people listed here, obviously. So we're specifying lots of model structures here. So firstly, there's an N which is indexing the category of N multi-complexes. So we can do anything from a bicomplex through any of the truncated versions all the way up to multi-complexes themselves. So we're going to think about that category of N multi-complexes. And then we're going to have a model structure for each R, where that's indexing the stage of the associated spectral sequence. So this is what we're talking about here. We're denoting it like this. This means n multicomplexes with the R model structure. And that's what we're specifying here in this theorem. And it says that there's a cofibrantly generated model structure on each of these categories. Well, on each of these categories and one for each R. Well, as I advertised that I wanted to do from the start, which is one where the weak equivalences are the E-quasi-isomorphisms. And we're doing, as I said before, just specifying the fibrations and the weak equivalences. So the fibrations, well, they are indeed specified by a surjectivity condition. And, well, it's the morphisms which are surjective on every page of the spectral sequence from 0 up to R. And then, as I mentioned earlier, in the cofibrations are just whatever they have to be to have the right lifting property. Well, the correct lifting property, that is to say the left lifting property. Okay, so we have all these model structures. Let me just comment on some special cases and so on. So, yeah, I mean, I said start from n is 2, in other words, start from bicomplexes. Maybe it's just worth thinking about n is 1 for a second, but there's not too much to say. So if n is 1, then you just have d0, that was the vertical bicomplexes, and you don't get a whole family of different model structures. You've just got the 0 model structure because, you know, the associated spectral sequence just degenerates, and in other words, all the R are the same, and you just get the R equals 0 model structure. And this indeed is the sort of motivating example that I used at the beginning, a sort of basic example of a model structure. This is basically just the projective model structure on unbounded cochain complexes. I mean, we've got these bigraded things, so we've really got a graded version of that, an extra grading in the story, but it's basically, it is just that. So there's a sense in which everything we're doing is kind of generalization of the projective model structure on unbounded complexes. And then the next case up, so the bicomplex case, where n is 2, that's something that had been worked out separately, so in joint work with Joanna Cerisi and Daniela Egas-Santander and Muriel Livanet. So we had done the bicomplex case together with the filtered complex case, which I'm not so much talking about here, in a previous bit of work. But the bicomplex case, you can now, if you want, view it as a special case of this generalization to multicomplexes, to n multicomplexes. And then, well, if there weren't enough model structures around, there are also some more. There's a variant model structure. So fix your category, so fix n, and fix your stage of the spectral sequence. So we're fixing n and R on that category with those weak equivalences, that there's a Quillen-equivalent model structure where the fibrations are characterized by a different surjectivity condition, and it's one related to R cycles, which I'll say a little bit more about shortly, rather than so it's related to the cycles rather than the pages up to the R stage. For those who don't know, you know, Quillen equivalence is sort of the way to say when model structures are giving you the same theory, the same homotopy theory. It's the natural motion of equivalent model structures. And indeed, sort of the way the proofs go, I guess the reason I'm really mentioning this variant is that actually this is the thing that we construct first, and then the one that's perhaps easier to state, or perhaps nicer in terms of having the surjectivity condition on the pages, you get that as a consequence of this one, in fact. So that's how it works out. Okay, so let me talk a little bit about what goes into this. Well, I mean, firstly, these are going to be cofibrantly generated model structures, and those are ones that are, are relatively easy to produce in some sense. They're sort of standard conditions. You have to specify sets I and j, which are called the generating cofibrations and generating trivial cofibrations, and then there's their kind of standard results, which give you lists of things you have to check in order for those to generate a model structure. So that's the game we're playing in general terms. Okay, and then here's maybe the sort of key idea that makes things actually work. And that is to find representable versions of R cycles and R boundaries. And on the rest of the slide in a moment, I'll say a bit more about exactly what I mean by that. But this is what I meant earlier on when I talked about using the freedom to change the cycles and the boundaries, as long as you don't change the pages. So we have that freedom if we want. We can change cycles and boundaries, we can play around with that, replace them by more convenient things, and that's what we do in order to build the model structures that we have. And the terminology that we use, for reasons that hopefully will become clear, is that of witness cycles and witness boundaries. So we replace cycles by witness R cycles for each R. We have, so we'll write ZW rather than just Z, and the W here stands for witness. And similarly for the boundaries. And the reason we want to do this is that the representing objects for these witness cycles and boundaries are going to be how we specify the generating cofibrations and generating trivial cofibrations of the model structure. So just to say what I mean by representable functors and which variants and so on. So sorry about the sort of plethora of indices here, but so this bold ZW, this is going to be the functor of witness R cycles, and the curly ZW is the representing object for that functor. And we have one for each N and each R, and indeed we have one sort of with a source by degree for each position in the bigraded object. So that's why there are so many indices here. And well, we sort of specify something for the cycles, something for the boundaries, and then really the thing we want is not exactly this thing for the boundaries, but somehow the data that's specified by a map, which on objects goes from witness cycle object to witness boundary object. On the corresponding functors, it will go the other way. So let me just put that up, and maybe it will become clearer. So the curly ZW is representing the bold ZW in the sense of taking maps out of this object in the relevant category. We have also the BW corresponding to the curly BW, and such that, importantly, we also have this map between them, and once we've applied these functors, we have sort of the image of BW inside ZW of an object. And sort of the main criterion for this being a correct choice of such objects and maps between them is that you do indeed recover the R page of the spectral sequence as, ZW over the image of BW. Okay, so this is kind of the key idea, and I want to say a little bit more about it. Again, really just for the cycles and then sweeping the boundaries under the carpet a little bit. And the reason I'm going to do it for the cycles is because it's kind of obvious what to do. I mean, it feels like a well, the obvious choice. I don't know if I want to say the canonical choice, but so I'm going to tell you exactly what the witness R cycles are and the sense in which they're sort of witness cycles. So, well, for 0, you just take the underlying object. And then what do you do for the R cycles from 1 onwards? So, well, you may not remember what I said about the formula for the R cycles in the spectral sequence of a multicomplex. But what I said was, you have an A0, and then you have a choice of an A1 up to AR minus 1, satisfying a bunch of equations. And they were exactly these equations that are written here. So what has happened here is that we've specified a choice of all that data. So before, the R cycles were A0 such that there exists these higher AIs like this. And here we've specified these witnesses so that A1 up to AR minus 1, they witness how A0 is an R cycle. So we've specified all those choices witnessing how something is an R cycle. So as I say, this is kind of an obvious thing to do, just like specify the witnesses rather than just require the existence of those elements. So that's kind of a reasonably natural thing to do. Probably trickier is to figure out a suitable choice of boundaries or how you map between the two in order to get the correct quotient. And I don't think there's really anything quite so canonical for that, but you know, you have to make a choice and check things. And I guess there's a couple of comments just going on here about this. I mean, I've only specified this on objects, but it's a functor in an obvious way, and you can restrict to n multicomplexes, the truncated version. So we have these witness cycles in all these categories as functors and for all the categories that I've talked about. Let's just go back and modify the diagram, the last one that I showed you. So this was, well, we have structure maps at least up to D3, but we might as well assume we have all of them. I haven't drawn them, but we could have a D4 and a D5 and so on. As you can see, I've taken my previous diagram and then drawn some new things on it and deleted a couple of things. So remember, when we had a 3 cycle before, we had an A0 such that there exists an A1 and an A2, satisfying some stuff that's supposed to be indicated here. And now we're doing the witness cycles. So for the witness cycles, what do you have? You have an A0 and a specified choice of A1 and specified choice of A2, such that the same things are satisfied. So that's all that's changed in terms of the, you know, so now we specify these witnesses, and that gives us a choice of a witness 3 cycle. And well, I haven't told you about the witness boundaries, so I won't do that, but it's quite easy to say something about the differential on the 3rd page. So before we had a differential specified on a class just of A0, and now we have to specify a differential on A0 and its witnesses, and the output has to be the class of such a thing. So again, it has to be a witness 3 cycle. And well, so the formula sort of extends in the obvious way, and you do see appearing here like D4 and D5. So there's kind of room for the next couple of structure maps to make an appearance in these formulas here. Okay, so that was to give you some idea about these witness cycles. And then I want to give you some idea about the representing objects for these things. So let's talk about the bicomplex case first. So there it's really nice, and because it's possible to just kind of draw pictures of all the representing objects that you need. And that's something that we did in the earlier paper that I mentioned. So in particular, the 2 here means n is 2, we're in the bicomplex case, and we can just do any R, and the representing object for the R cycles is a staircase bicomplex like this. So I should explain what this picture means a little bit more probably. So each of these bullets and also this asterisk here, they just stand each for a copy of the ground ring, a free module of rank 1 over A, and each of these arrows here is just an identity map. So that's what this picture means. And so you have this staircase, and you just take a longer staircase for higher R, and that gives you a simple representing object for the witness cycles. And I haven't put the picture here, but it's not too hard to make a similar picture for the witness boundaries in the bicomplex case. There's a bicomplex which I sometimes call the box under the stairs bicomplex. It has kind of a staircase and then a box and then some more stairs. And anyway, the point is that in the bicomplex case, you can draw very explicit pictures for all the representing objects, kind of for the relevant map that you need between cycles and boundaries as well. And that's how we approached these representing objects in that earlier paper. I'm going to show you a couple of pictures of what happens when we introduce another structure map. So let's just go up to n is 3. So this means we now have a multi-complex which has a D0 and a D1 and a non-trivial D2 now, but nothing higher. And now I'm just going to show you the representing objects for very small values of R. And even then, I'm not going to properly explain everything that's going on in these pictures. This is mainly here to just convince you that this is not the right way to do things in this case. But let me just say a couple of words about what's going on here. So even for the 1 cycles, once we have a D2, so the D2s are these longer arrows here, things are already quite a bit more complicated than they were for bicomplexes. So for bicomplexes, we would have just had a staircase which doesn't really have any stairs. It has a single horizontal step. So we would have just had this little part here. But as soon as we put in a non-trivial D2, well, firstly, D1 squared is no longer 0. So you get these iterated D1s, and you get this sort of thing, this representing object continues infinitely to the left here. And then you also get D2s, and it's already looking a bit complicated, and that was just for the 1 cycles. And then if you go to the 2 cycles, well, I'm not really going to explain this picture, but you can see that, again, we've got something that's sort of infinite to the left, and now we've got kind of 2 rows in this picture. And if we had more structure maps, we would have more structure maps in this picture, and also something more complicated, and so on. So this is probably not the way to do it. That is to say, we want these representing objects, but we don't really want to try to get them by drawing pictures and explicitly giving the complexes in that way. So let me just say a few words about what we do instead in this multi-complex case. So instead of sort of drawing the witness cycle objects, we construct them by an iterated push out. So, so firstly, where do we start in doing this? So that's kind of clear. So that the witness 0 cycles, they're just the same as the 0 cycles, and they're just the same as the underlying object. So we're just trying to specify an element in an object. So that's represented by a free object on one element, right? So you start from a free object on one element. And then what do you do for 1? Well, what are the witness 1 cycles? the witness 1 cycles, they're the same as the 1 cycles, and they're the kernel of D0. So you want a representing object for the kernel of D0, and well, because of the kind of covariance, this contravariant functor thing, that ends up being represented by this push out, this co-kernel of a map representing D0. So that's how you start for 0 and 1, and then you have to figure out how to recursively define the witness R cycles for higher R. So here, I won't say too much about the details, but roughly, it's easy to say roughly what we're doing here. So I'm constructing this thing as a push out, this diagram. I'm imagining that I've already constructed this one, which is the R minus first one. And what am I doing in this push out? Effectively, we're kind of adding one new generator here, and we're gluing it in doing this push out by one new relation, which is the kind of new relation that you have in the witness R cycles when compared to the witness R minus 1 cycles. So that's how we get these witness objects. And then, well, I probably should just sort of tell you how you use them to make the generating cofibrations and trivial cofibrations of the model structure. I mean, I've only told you about some of these ingredients really, but it'll give you an idea. I mean, for the J here, I've told you all about this because you just take the map from 0 to the witness R cycles, and I've kind of explained about that. And then for the other one, well, I haven't really described this witness boundary object or the map, but I've tried to explain what it's doing in the story. And these are basically the sets that you take for your generating sets for this cofibrantly generated model structure. I mean, maybe not exactly, there's a slight tweak that's coming here. So the I is exactly the right thing, and then it turns out you take not exactly JR, but also J0 for the J. So you check that those give you those sets of a cofibrantly generated model structure. And then, well, you can kind of see, I guess, that from the form of the J's, which I have told you about, that this model structure is going to be one where the fibrations are characterized by surjectivity on the object itself and on the witness R cycles. So that's what I meant when I said something about some condition related to R cycles. I meant surjectivity on these witness R cycles. So that's the model structure you get first from thinking about this sort of thing. And then there's a sort of maybe a way of putting things together that allows you to get the one that I put in the theorem. So when I stated the theorem about the model structures, I stated the model structure where the fibrations were surjective on the pages of the spectral sequence up to the rth page. And you can get that one from this one by kind of putting together, you put together this I and J with the lower J's, something like that. So anyway, you can do that. All right, and then the last thing I wanted to just talk about a little bit is comparing these different model structures. So then we've now got lots of model structures around, and I can say something about comparing when I change the n. So this is for fixed R, this theorem. So I'm not changing the stage of the spectral sequence here, but I'm comparing different categories that I have. And so we have here, we have an R, which is fixed in all of this, and that's a stage of the spectral sequence. So we're thinking about the model structures with E-quasi-isomorphisms. And I'm comparing what happens when I vary the n. So here I've got n multicomplexes, and here I've got L multicomplexes. And there's an adjunction, which turns out to be equivalence relating these. So as you vary n from 2 all the way up to infinity, you're getting Quillen equivalent model structures. We say a few more words about that. Well, firstly, I mean, the main idea of how you can get this is what's written here. So there's a way of thinking about n multicomplexes as modules in vertical bicomplexes, modules for a DGA. And then you can compare the DGAs and these functors, from that point of view, the functors that compare what happens when you change n here, you can think of those as kind of restriction and extension of scalars related to changing between these different DGAs or the corresponding module categories. So that's sort of a comment about how you set this up. And then maybe just to sort of comment, putting this into context a little bit to finish up. So there's a sort of case of this which is very classical. So we could think about bicomplexes compared to multicomplexes. So in other words, take the extreme case where n is 2 and L is infinity. So we're comparing bicomplexes with their homotopy coherent version, which would be full multicomplexes. And then this result that the model structures are Quillen equivalent for R equals 0, that would be a kind of classical thing. It would be saying that, you know, the standard model structure that you do with respect to kind of usual quasi-isomorphisms, that's Quillen equivalent if you do it for some algebraic structure or the kind of infinity version of the algebraic structure. So from that point of view, this is generalizing that result in two different ways. Firstly, it's saying that the same is true for all these intermediate categories in between, all these truncated versions between bicomplexes and multicomplexes. And then it's also saying it's true for every R. So we could look at these different model structures, not just the R is 0 one, but the R one for the rth page of the spectral sequence. And the same result is true there. And I think I'll stop there.
Thank you for this great talk. Maybe someone has questions? So, okay, well, Sarah, I have to tell you, there were some questions in the chat and I was trying to answer them, but maybe...
I will,
but
let me just...
well, it was about the, I can summarize, it was about the witness, the Z, the witness. Mm-hmm. So how can we, okay, what is the precise question? Yeah, so how do you specify the witnesses? I think the main point that maybe you didn't mention is that of course, these new witness cycles and boundaries, if you do the quotient, you recover the spectral sequence, right? Or
yeah, exactly. So let me go back. Yeah, that's right. So I mean, this is sort of the a required condition. So there are probably lots of choices here. I mean, as I mentioned, somehow the choice for the cycles, it seems very canonical. You know, the cycles are things, elements with such that there exist the witnesses. So the natural thing to do is just specify those witnesses. Mm-hmm. For this one, I didn't really tell you what you do, and for the map between them, I didn't give the details. And there, I'm not really sure whether there's a kind of canonical choice. Maybe there are lots of choices, but you know, you have to specify things so that you recover the R page of the spectral sequence. So I would say that there's a pretty canonical kind of choice for the witness cycles, and then you make convenient choices in order to have have this, to have both things represented. I mean, you need in the end some choice of what's on top here, and then some choice of what's on the bottom here, and all of this, at least for the way we're producing the model structures, all of this done by representable functors, because then you have to use the representing objects to specify key data that builds the model structure. I don't know if this answered the question.
I think so. I don't know who originally asked the questions, but I think this clarifies a lot. Any more questions?
I have a question. So, I mean, it's clear to me why you define the weak equivalences in the way that you define them, but it's less clear to me, like, why this particular choice of vibrations in the model category? Like, what's the driving idea? Like, what are you trying to achieve when you define the vibrations, sort of?
Yeah. So, I mean, there's probably various different answers to that, and of course, you know, there could be other model structures with different choices. I mean, I guess one kind of answer is the sort of theme here that we're generalizing the projective model structure on chain complexes. So it's sort of natural from that point of view. In terms of, you know, motivation, like how I ended up getting into this story, it was related to this derived A infinity story, and there, yeah, I mean, there you're building kind of. So Sagava's motivation for that was to do with classifying DGAs up to quasi-isomorphism, and if you can kind of think about that story as one about minimal models and A infinity structures. If you're working over a field, the point is about what he was doing was that if you try to do that story over a general commutative ground ring, then you're led to this extra grading, extra resolution direction, and the derived A infinity story. Okay. And so he has resolutions there which are sort of like projective resolutions, but you know, you would like model categories or some way to understand exactly what's going on a bit more conceptually. At least I would like that, to understand that story, which is ultimately a story about classifying DGAs up to quasi-isomorphism, sort of to put the derived A infinity structures into a conceptual framework, which for me meant model structure, where the things that Sagava's working with are you know, cofibrant replacement, essentially. Okay, thanks. Does that answer it?
Yeah, a little bit. Yeah.
I've got a very, well, we were told yesterday there's no such thing as a stupid question, but let me try again. So in the same way that you've got multi-complexes as dual number infinity or whatever things, do you think there's a chance that these model category structures might also be produced by some general machinery in some infinity transfer model structure language, or I don't know?
Yeah, I mean, maybe. Of course, I'm not maybe the right person to do infinity language stuff, or at least I'm still learning it. Alice, who just asked the previous question, has a nice setup to do with spectral sequences, indeed multiplicative spectral sequences associated to a stable infinity category. Feel free to correct me when I say something wrong, Alice. But she's thought about these kind of things, and yeah, I mean, maybe you could have a framework where you would have, I don't know, perhaps model structures on the category of spectral sequences themselves, and then transfer to all sorts of places. But I don't really know. I mean, if you just have spectral sequences, then you kind of don't really have room for things like the witness objects, or at least, yeah. So I don't really know.
Okay, maybe one last question, if there's. Okay, maybe, well, I have many questions, but I think I'll send you by email. It's better that everyone has 10 minutes break. So thank you, Sarah, for the great talk. Thank you very much.
Thank you, everybody.
And now, yeah, we have 10 minutes, and at 11, we're back with Otzi Boys.